Now let's proceed to the Stirling number of the second kind. This is connected to the idea of surjective mappings in the previous two videos, but this time we are talking about the distribution of n distinct objects from one set to m boxes or m objects on the second set, where those boxes or objects are identical in nature, and considering that none of those boxes are empty. Let me write here the definition for Stirling number. Let S n of m denotes the Stirling number of the second kind, and is defined as the number of ways of distributing n distinct objects, okay, into m identical boxes or objects on a second set, so that no box is empty. Okay, so again, similar to what happened in the discussion for the number of surjective mappings or surjective functions we can have for one set to the other, none of the boxes in the second set would be empty, but it strictly focuses on distinct, meaning in the previous examples we had the boxes being non-identical, meaning they are very there is a distinct difference, or there are observable differences between them, say for example of different size, different color, different shapes. But this time, what if those boxes are actually identical in nature? This is where it gets even more interesting by distributing that. Take note that n here is the cardinality, say for example, of your set n. Okay, cardinality, your first set, the number of objects, and your m here is the cardinality of your set n sub m, would be the number of boxes. Okay, so we're going to talk about some of the examples later on in this, and how do we solve this form using this formula we're going to present here, the formula for the number of or the Stirling of the second kind. It also known as Stirling of the second kind because we are to distribute again, or separate or partition the number of objects in the first to meet the second set, number of elements in the second set. That's why it's number of the Stirling number of the second kind. We also have the Stirling number of the first kind, but let's talk about the Stirling number of the second kind. Okay, this is a formula for getting that. We'll have here 1 over m factorial of the summation of -1 raised to k m combination k m minus k raised to n, where k is 0 to m. Okay, this is the formula. So once we know what is n, what is m, simply substitute that. Now, before we end this video and proceed to the properties and some examples later on, I would like to take your attention to this portion here. If you can still remember, this is actually the formula for the number of surjective functions or surjective mappings in the previous two videos. Okay, why do we have this as a factor for it to become Stirling of the second kind? Now, let's talk about the idea that m is identical. Okay, in the previous example, in the surjective mappings, these objects are the objects in the second set are distinct, meaning there are differences, and it's clear if I place something here, the other one will have a lesser, okay, something like that, because it's very obvious which boxes will have more than the other. But this time, the reason for that factor is that the idea of distributing distributing the objects into identical boxes follows the idea of permutation multiset. Take note that if we have before the formula for permutation multiset, our denominator will talk about the number of times a certain object was repeated, right? So we're going to take the factorial for that. So if there is only one, that's why you have m. That's why we have this as, because if we can rewrite the formula as f, the number of surjective functions or surjective mapping, over just m factorial. This indicates permutation multiset. That is the only factor that is different. So from our number of surjective mappings or surjective functions, you can take the number of the Stirling number of the second kind just by simply multiplying it by 1 over m factorial. We will have an example to this later, but in the next video, we'll be talking about some important properties for Stirling number of the second kind, so we can actually guess, or not guess, actually provide some idea on how to illustrate examples later on, especially when the number of elements in n and m are very large. Thank you very much for watching.